Hi, my name is Maggie Monahan, and this is my Lab 3 video, Magnetic Field of Permanent Dipole Magnets. The purpose of this lab is to determine the distance dependence of the magnetic field due to a small bar magnet, and to compare these measurements to the distance dependence predicted for the magnetic fields derived from the Biot-Savart law. Also to determine the magnetic dipole moment of the magnet. Some fundamental concepts that will be used in this lab are the Biot-Savart law, magnetic fields, and magnetic dipoles. For this lab, first we had to download a magnetometer app on our phone and then align the phone with magnetic north. Then we had to determine the exact location of the sensor in the phone. We did this by moving our bar magnet at different distances away from the phone. Then measured the distance between the magnet and the phone to produce magnitudes of 20, 70, 120, 170, and 220 microteslas. Next, I measured the off-axis perpendicular magnetic field, using a similar procedure to the one described above. I observed a couple different things while taking these measurements with the bar magnet and the phone. First, when the magnetometer is far away from the magnet, it measures a near-zero magnetic field in the x direction. Secondly, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. On this slide, you can see the data collected for the distance the magnet was away from the sensor and the corresponding magnitude of the magnetic field. First, for the on-axis data, measured at 20, 70, 120, 170, and 220 microteslas, and at the off-axis field and their corresponding averages. Also, there is a graph for the ln of b of x versus the ln of r. The next step in this lab is to use the data we found when moving the magnet at different distances away from the sensor and the corresponding equation found on the ln of b of x versus ln of r graph in order to calculate the magnetic dipole moment. We can use the equation y equals negative 3.0371x minus 14.612. The y equals mx plus b equation from the graph is equivalent to the equation ln of b equals ln of k plus n times ln of r. So we can find that n is equal to negative 3.0371. Rearranging the equation, we can find that k is equal to e to the negative 14.612, which is equivalent to 4.509 times 10 to the negative 7th. Next, we need to solve for mu, which by rearranging the equation for k equals k times r to the n equal to mu naught divided by 4 pi times 2 mu divided by r cubed, you can find that mu is equal to 2.453. The next step in this lab is to use coding aspects in order to be able to compare the distances and the values we found while using our physical calculations to the formulas and the principles used in the Biot-Savart law. So here we can see that a magnet is created and placed at the origin, and also the mu found in the previous slide is inputted to be our magnitude of the magnet moment. Next, a function is created for the magnetic field. Next, many different arrows will be created in order to see the magnitude of the magnetic field at that specific distance from the bar magnet. Here we can see a visualization of the code. The bar magnet is represented by the gray cylinder. The orange arrows represent the B field on axis. The blue arrows represent the B field perpendicular to the bar magnet, and the green arrow represents the B field at a 45-degree angle. So, after going through the details of this experiment, there are some questions associated. What if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? The magnetometer's x component would not have been close to 0 at the start of the experiment, So because of this, the Earth's x component in addition to the magnet's x component would result in a much larger x component values, which would definitely change the outcome of this experiment. Also, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? If this were to happen, there would be a greater magnetic force which would make the measurements much greater. Thank you so much for listening.